some challenges as the question types that we've been covering in the class don't seem to really be matching up well with what you're seeing in my math lab. And so I wanted to walk you through the homework for this section to try to help answer some questions and to just give you guys another tool to be able to help you on the Chapter 4 quiz and on the material that you'll need to know for the final exam. Okay, so here's the first question. One thing I'd like to point out is on every question there is going to be some numbers in this corner. And what that tells you, it's Chapter 4, Section 3, Part 1. So it gives you an idea of where in the slides this material came from. Okay, so for this question, what is wrong with the expression the probability of event A plus the probability of event not A equals 0.0 or 0.5? So let's review what this equation is actually saying first, and then we'll figure out what the answer is based on that. So the probability of A is whatever outcome you're hoping for. Not A is by definition A's complement. And by what that means is that not A is anything that occurs that is literally not event A. And so basically you have two options. Either event A is going to happen or not A is going to happen. And based on that, by definition, that's all the possibilities that there are, either A or not A. And so rather than adding to 0.5, like it says here, they must by definition add to 1, because together they represent 100% of the possible outcomes. Either A happens or not A happens. So let's look at our choices. Based on the rule of complements, the sum of PA and P not A must always equal 1, so that sum cannot be 0, or not be 0.5. Yes, that's what we just said. Let's look at the others. Here it's telling us that the sum must be 0. We just said that that is not the case. The sum must be 1, so we can rule out this answer. And here, these are just not the rule of complements. The sum of the event A plus not A does not equal one or the other. It always equals 1. So the correct answer here is A. So let's go through. Okay. And we'll move on to the next question. Okay, next question comes from Chapter 4, Section 3, and we're going to decide whether two events are disjointed. So let's first figure out what a disjointed event is, and then from there we can review the rest of the question and make an answer. So when something is disjointed, what that means is that they are not connected. And it also means that they cannot occur at the same time. So for example, in the last problem we had event A and not A. Those two things are always disjoint. Any event and its complement must be disjointed in the sense that they can't happen at the same time. If event A happens, well then certainly not A can't happen. And so, okay, now let's read through the question and see whether we can apply what we just said to this to get our answer. So we need to decide whether the following two events are disjointed, meaning that they can't occur at the same time. So randomly selecting an animal with both eyes green and randomly selecting an animal with both eyes brown. Well, here, one of the questions that I would have looking at this is whether they're talking about two different animals or whether they're talking about the same animal. But let's assume that it's the same animal for the purposes of this. So the animal can't have both eyes green and both eyes brown at the same time. So we would consider these two events to be disjointed. So let's look at what we have here. So we just said that we need to decide whether they're disjointed. So we're going to say yes, they are disjointed, meaning they can't happen at the same time. You can't have both green eyes and brown eyes at the same time. And is that And we also said that it's because the events cannot occur at the same time. That's the definition of disjointed. So let's check our answer. Great. Okay, so we will move on to the next question. Okay, question 3 also comes from section 4.3. And in this question, a research center poll showed that 84% of people believe it's morally wrong not to report all income on tax returns. And we want to know, what is the probability that someone does not have this belief? Okay, so here's how to approach this question. They're telling you that 84% of people believe it's wrong to not report that income. And what they're asking you to find is the probability that someone doesn't think it's morally wrong. So let's look at the information we're given. We're told that 84% of people think that it's morally wrong. So knowing that the people that think it's morally wrong and those that do not together must add to 100% of people, if 84% believe it's morally wrong, then if we take from 100 and subtract 84, we're left with 16% that must not share that belief, in the sense that they don't believe it's morally wrong. That 16% we can convert into a decimal or a probability, which is what the question is asking for, by dividing by 100. So if you take 16%, which is what you got when you subtracted 84 from 100, and divided that by 100, you'd get an answer of 0.16. And let's see if that is correct. It is. So again, for this question, you needed to find the relative percentage based on the people that did not, or that believe it's morally wrong, to find the percentage of people that did not believe it's morally wrong, and then you need to divide that percentage by 100 to turn that into a true probability, which is always a decimal. Okay, let's move on to the next question. Next up, this question also comes from 4.3, a little further towards the end of that section. Okay, so the following data summarizes results from 1,000 pre-employment drug screenings. If one of the subjects is randomly selected, we want to find the probability that the subject had a positive test result or a negative test result. Okay, this question is a bit of a trick question. They are giving you the 1,000 people that had the pre-employment drug screenings, and they're also giving you how many people fell into what categories. But the thing is, you don't even need any of that information to answer this question. Let's look at what they're really asking us. They want to know, we want to find the probability that the person who's randomly selected either tests positive or negative. Let's look at this. There's only two options, that they're either going to test positive or negative. So there is a 100% chance that the person is going to either have a positive test result or a negative test result. Similar to the last question, if you know it's an 100% chance of that happening and you divide that by 100 to turn it into a decimal, you'd find out that this is 1.0, which means that it's absolutely certain that the subject will either have a positive test result or a negative test result. And let's check our answer. Great. Okay. Let's move on to the next question. We've actually already talked about this question when we had the problem dealing with the probability of A and the probability of not A. And we said that those two events were disjointed and that they cannot occur at the same time. So I expect when I pull down this pull-down menu that disjointed will be one of the options. And it is. And let's check our answer. Yep, great. So these events cannot, by definition, occur at the same time. Okay, next. This notation. And we learned about this in section 4.4 on the multiplication rule. This, and I told you guys in class, that this indicates the probability of event B occurring. And I said that this line represents the words given that event A has already occurred. So again, This notation means the probability that event B occurs given that event A has already occurred. So let's find that. Option. Well, this is definitely not it. It's not C and it's not D. What about B? The probability of event A occurring given that B has already occurred. No, we said it's the other way around. B occurring given that A has already occurred. So our answer is going to be option A. Great. Okay, let's move on to the next question. Okay, this question also comes from section 4.4. So for the given pair of events A and B, we are going to complete multiple steps related to this question. So when a page is randomly selected and ripped from a 21-page document and destroyed, it is page 6. When a different page is randomly selected and ripped from the document, it's page 13. So the first thing that we need to understand is we need to understand whether A and B are independent or dependent, meaning that do they impact one another or not. So let's think about this. For A here, a page is going to be randomly selected and ripped from a 21-page document and destroyed. So the probability there of drawing that page 6 is 1 out of 21, because only 1 out of the 21 pages is page 6. And you'd find that you get a probability for that of 0.04, let's see how many, well, it doesn't give me how many decimal places, so we'll say 0.0476. Now, for the second part, if the page in event A already happened and it was already taken out, you now don't have 21 pages anymore in your document, you only have 20. And so here you need to adjust your total number of pages that are left to account for the page that was already ripped out and destroyed in part A. So for B, it's not 1 over 21, it's 1 over 20. And when you do out that math, you get 0.05. So if I take 0.05 and multiply that by 0.07 or 0.0476, I believe it was, I'm going to get 0.00238. Okay, so let's and actually what we just figured out is part B. So, and as we just discussed, they do have an impact on one another because we needed to make an adjustment to figure out part B based on what happened in event A. So now let's go ahead and answer the questions. So part A, we're going to say that the two events are dependent because the occurrence of one affects the probability of the other, which we just saw. Great. All right, and now the probability of them both occurring should be, let's see, round to 4 decimal places. Okay, let's see. Great. Okay, so that's how you solve this question. You need to look at what they're giving you, and I know it's very wordy, and that makes it extra confusing because you feel like there's a lot of information being given to you in these problems that you don't need. And what I recommend is that you focus on the information that you do. For part A, you're trying to figure out what the probability is here. For part B, you're trying to figure out what the probability is there. And then you're trying to answer the questions and figure out whether you need to add them together or multiply them or so forth. Please bear with me for one moment. I'm just going to plug in my computer, so hold on while I do that. And then we will move on to question number 8. So I hope that this session is helpful for everybody. You guys will have to let me know if it is, but I can appreciate the fact that the questions are very wordy and that makes it extra difficult to get through them. But, you know, I know it's easy to say, but you really have to almost train yourself how not to get lost in all the words, but to only pick out the information that you really need. Okay, so let's move on to the next question since we did question 7. Okay, let's move on to question 8. Okay, So the principle of redundancy is used when system reliability is improved through redundant or backup components. Okay, what does that even mean? And no, this is not a concept that we talked about in class at all. So it's not something that you would have learned in class from me. What they're talking about here is basically the fact that if you want to improve the reliability of something, the more redundancy you build into it, the more likely it is to happen. So for instance, if you're trying to get people to wash their hands consistently, you may put up signs by every sink and every bathroom stall. And hopefully through that redundancy, you get the message and suddenly everyone starts washing their hands. So although not the best example and not the example in this problem, it kind of gives you an idea of what they're talking about in theory here. And no, this principle of redundancy is not a mathematical concept in the sense that it isn't something that's covered in our textbook. Okay, now that we've talked about all that, let's read the rest of the question. We're going to assume that a student's alarm clock has a 6.6% daily failure rate, and we're going to complete parts A through D. Okay, so first we want to know what the probability is that the student's alarm clock will not work on the morning of an important final exam. All right, first thing to point out here, it doesn't matter whether it's an important exam or not. Your probability of having a failure remains the same whether it's a Saturday or a Monday, and regardless of what's going on. So they actually give us this number, but they give it to us in a percentage. And we're required in part A to turn that into a decimal, or to make it into a probability. So you're going to take that 6.6% and divide that by 100 to turn it into a decimal. So this will be 0.066. Okay, moving on to part B. If the student has two such alarm clocks, so basically two alarm clocks that both have the failure rate of 6.6%, what is the probability that they will both fail on the morning of an important final exam? So we said that the probability of any one failing is 0.066. So to do two clocks, you'll take 0.066 and multiply it by 0.066 to represent your second clock. And you are going to round to 5 decimal points, and you will get an answer like this one. Okay, great. All right. Now, this next question, they want it to do for 3 alarm clocks. So this was 1 alarm clock, 2 alarm clocks. Now we're going to do 3. So you're going to take 0.066, I should say, and you're going to cube that. So you're going to multiply it by itself 3 times. Okay, and here you're also going to round to 5 decimal places. Okay, great. Okay, and what they want to know here, and this last part, part D, don't get tripped up by this. Do the second and third alarm clocks result in greatly improved reliability? Okay, so what they're asking is, here you have a 6.6% chance of missing your alarm clock. Here you have less than 0.5% chance of your alarm clock not going on. Here you have a fraction of that. So basically, with the more alarm clocks you add, the lower your probability is, the smaller your probability is of not getting an alarm clock. So we want to know, do they improve reliability? Yes, because a total malfunction would not be impossible, because this number is not 0, but it would be very unlikely. Okay, so great. There's question 8, and we've completed all the parts. Okay, next question. Also from section 4.4 on the multiplication rule. A tire company produced a batch of 5,100 tires that included exactly 230 that are defective. We want to know in part A, if 4 tires are randomly selected for installation on a car, what is the probability that they're all good? Okay, so for this problem, there is a little bit of math that needs to be done. So first things first, let's calculate our defect probability. So we're given that 230 out of 5,100 cars are defective. So if I take that 230 and divide it by the 5,100, I get what do I get? 0.045. Now, if 230 out of 5,100 cars are defective, now I need to figure out, hold on one moment. I need to write down some numbers here because I'm going to need them as we're moving forward. All right, so let me get our probability of defective here, 0.045. Okay, so now we need to figure out our probability of being good. So here we're going to take from our 5,100, 230. So if you take from 5,100, 230, you're left with 4,870 tires being good or not defective out of 5,100. So if I take that 4,870 and I divide that by 5,100, I'm given a probability of the tires being good at 0.955. Okay, so now that I have my probability of them being good and my probability of them being bad, any one tire, now we want to figure out what is the probability of 4 being, that if 4 tires are randomly selected that they're all good. So we've already figured out that the probability of any one tire being good is 0.955. So if I take that 955 and multiply that by itself 4 times to represent each tire, I wind up with 0.832, that they are all good. Oh no, what has happened? Oh no.